video is intended to provide some background on assessment methods that are used for TMDL analysis. What are the objectives of assessment? Well, one is to determine the characteristics of one or more pollutant loads. Second is to determine the reduction in load that is necessary to meet water quality standards. So if we can estimate how much load is occurring, and if we know what the water quality standard is, we'd be able to determine how much the load reduction is necessary to meet the water quality standard. Want to identify from the assessment as to what the different possible pollutant sources are for the particular pollutant of interest or of concern. And then hopefully be able to assign to each of the potential pollutant sources an amount of the load that is occurring. And finally, to estimate the improvement in water quality that would ensue from implementation of best management practices. So if we can quantify how much load is occurring, we can identify the sources of the pollutants, that is, pinpoint where the sources are. If we then propose to put in best management practices to remediate or alleviate those pollutants, then to be able to determine how much reduction in load will occur, and from that knowing determining what the water quality improvements will be. So the question is, what a method of assessment is appropriate for a particular situation? And one principle maybe that we should follow here is that we want to keep the approach as simple as possible. The method selected needs to be supported by information available, so you need to have appropriate amount of data available to apply the particular method. One thing you do not want to do is to go in to a group of stakeholders, tell them what's going on, and then be asked a question about, well, where's your data from? And you need to have data that's going to support your conclusions. And I think this next comment applies directly to that the method that you're going to use needs to provide information that will be fairly easily understandable by the stakeholder community, and also a method that's going to be trusted by the stakeholder community. Again, one thing you do not want to do is walk in front of an audience of stakeholders and have and basically overwhelm them with information that is not understandable, because then you're not going to be viewed as being trustworthy. And then, of course, the method needs to be user-friendly, the user being you, the person that's doing the analysis. So there are I've identified two categories of methods. There may be other method categories as well, but this is the way I've got it laid out. And first category, these are methods that are based on basically on monitoring data, or based on information that's gleaned from the literature. And with these methods, the interest is mostly in what the load is from a watershed. These methods typically do not provide details of what's going on inside of a watershed. That is, they're more difficult to directly be able to pinpoint where a pollutant is coming from. And that does not mean, and you'll see in the further discussion, does not mean that these methods will not be suitable in attempting to identify pollutant sources. And to use these methods, generally you need to have detailed flow data and detailed pollutant concentration data. The second category of methods are methods that are based on watershed scale modeling. And most of the models that I'll discuss, and the ones that have typically been used, do provide some detail of what's happening within a watershed. For instance, a model might break up a watershed into different land uses, and from that be able to calculate the load coming from each of those land uses. The other thing is that many of the models available, or among those models that are available, these range anywhere from simple spreadsheet models to models that require significant computing power. So in this presentation, I'm going to cover Category 1 methods in this first section. A second video will follow up from that to discuss Category 2 methods. So Category 1 methods depend entirely on monitored flow and pollutant concentration data, or as I mentioned before, they might actually just depend on literature values. But of course, those literature values also do depend on monitored information, both flow and pollutant concentration. So they are actually, the information derived from the literature is information that's derived from monitored data. Generally, for Category 1 methods, when you're using monitored data, the flow is, sampling is usually continuous, but almost always the pollutant concentration is not continuous. Now, this is changing over time as new sensors are being developed that allow you to make measurements in real time. An example sensor would be the one that quantifies, that is capable right now of measuring nitrate concentrations in stream water. So YSI probe or other types of probe sensors that can do this provide then for continuous monitoring of chemistry. When both flow and pollutant sampling are both continuous, then the development of or quantifying load coming from a watershed is very easy. When the flow is continuous and the pollutant sampling is grab samples, periodic or event-based sampling, then statistical methods are usually necessary to be able to come up with what their load relationships are. So Category 1 methods are useful in determining what the current conditions are or what historical loads are. They're not methods that can be used to predict future conditions. These can be used to quantify loading from a watershed. They can be expressed in units of per area basis, so per acre, per hectare, per square mile. Usually it'd be per acre or per hectare. You can take these results, let's say, from a particular watershed and compare it to what is found for other watersheds in the same region, or even other watersheds in other locations around a world. These loads that are then derived can be used in trying to quantify the possible effects on downstream receiving waters. So if you're quantifying the load coming from a channel reach or from a river reach, creek reach or something like that, that load can be used to determine what impact it will have, let's say, on a lake or reservoir downstream, and what effect that would then have on the beneficial uses of that downstream water. As I've already mentioned, these methods cannot be used to predict the effects of future land use change. Okay, so the Category 1 methods generally will provide an aggregate load number, and so then these will not identify directly the individual sources of a particular pollutant. And the details that you have for a watershed will be whatever scale you are doing the monitoring at. So if you're monitoring at the outlet of a 5 square mile watershed, basically you'd be able to say from your estimate what the load is coming from that 5 square mile watershed. You will not be able to say where within that 5 square mile watershed the load is coming from. That would require additional analysis, which I will discuss later. And if you implement a BMP in a watershed, you should try to monitor, and you want to evaluate whether or not that BMP is effective or not at what it's supposed to do. Then you need to monitor that BMP at the scale that's associated with that BMP. If you put one BMP inside of a, let's say, a saturated buffer inside of a 5 square mile watershed, there's very good likelihood you will not see the benefit of that particular BMP just because of the differences in scale between the area represented by the BMP and the area represented by the watershed. So some example Category 1 methods are load duration curve, the Flux model, which is developed from the U.S. Corps of Engineers. They developed that mainly to look at impacts of upstream waters on reservoirs. The load estimator method, which is developed by the U.S. Geological Survey, regression of pollutant load and flow method. And then there's also a category, as I mentioned earlier in the video, about literature values to estimate loads. So basically, you'd find a table and a research article or some guide document that would tell you or give you guidance about how much pollutant load might come from a particular agricultural management practice, forestry management practice, urban management practice, or suburban management practice. So that's among these methods that I've mentioned, we will be using the load duration curve, the Flux method, and this last category of literature values to estimate loads within the course. So load duration curve, here's an example of a flow duration curve, and I'm going to go in more detail on this in lecture. But this illustrates the fraction of time that a particular flow in a creek, this one was Salt Creek near Greenville, Illinois, the fraction of time that that flow is equaled or exceeded in that stream or in that creek. So the 440 cubic feet per second that is shown there would be the flow rate that would be exceeded 60% of the time in that for that creek. Other numbers that are illustrated on there, 90% of the time 130 cubic feet per second would be exceeded. 954 CFS would be exceeded 40% of the time. 3,270 cubic feet per second would be exceeded 10% of the time. So the higher the flow that you're looking at, the less percent of time that flow would be equaled or exceeded. From the flow duration curve, you can derive a load duration curve, and this is a graph that has the same horizontal axis on it. Vertical axis would be the chemical load coming from, for a particular pollutant that would be passing by the point where the gauging station is associated with the flow. So using the example from the previous slide, this is for the same creek or same river system. 440 cubic feet per second was exceeded 60% of the time. If our water quality standard is 10 milligram per liter, then for that water quality standard, we would be expecting that 11.8 tons of nitrate would be passing by the gauging station per day. And this brown line that you see there is the target or water quality standard that you would have based on the 10 milligram per liter for that creek. This does not have superimposed on it the actual monitored data. That's another step in the process. And this will be covered again in lecture. The Flux model was developed by the U.S. Army Corps of Engineers and is a interactive program. Basically, it's a spreadsheet program, Excel spreadsheet program for making estimates of the loads of nutrients or other water quality constituents such as TSS or other constituents of concern. This was developed as a companion tool to the bathtub model. We will be using the bathtub model to model lake water quality and also lake water balances. Bathtub model was also developed by the U.S. Army Corps of Engineers. The Flux model has 6 methods or 6 algorithms for estimating loads. And these are statistical methods. Actually, it's been upgraded. I think it has 7 or 8 methods, but in this class, we'll only be using 6 of those. It basically maps the, again, you need to have monitored flow data and monitored either grab samples or continuous concentration data. And what it does is it then maps the relationship between flow and concentration, and it uses that information to be able to come up with estimates of load passing by a point and also quantifying the uncertainty in those estimates. Has the ability to take data and put into different stratifications of flow. So you could look at different flow categories between very low flow to very high flow and break that range up into different segments so you could actually quantify how much of the chemical load is occurring within each one of those flow categories. You could also break the data into seasons, so you could evaluate how much load is coming during the spring, how much is coming through the summer, how much is coming in the fall, how much is coming in the winter, that sort of thing. So the model requires constituent concentrations. These can be, they can either be grab samples that are taken on a periodic basis. They could be taken on a event basis. So you might take a grab sample once a week, for instance, during base flow conditions. And then during high flow, during storm events, you might take more samples. And of course, you need to know when the data is collected. You need to have corresponding flow measurements. And it's very helpful, of course, if you have a complete flow record for the period of interest. So you want to have a continuous flow record if at all possible. The 6 algorithms that are available, and I mentioned already there are 8 methods, but only 6 are currently active, and we'll only be using those 6. There's a direct mean loading method. There's a flow-weighted concentration method. There's a modified ratio estimate method, first-order regression, second-order regression, and regression applied to individual daily stream flow. Each of these methods provide different levels of accuracy, and we'll use all of them, or at least the model automatically gives you estimates of load for all 6 of these estimation methods, and then it's up to the user to evaluate the output to determine which of the estimates is best. And there are statistical measures that are provided by the calculations to help guide you in choosing which of the methods are best. Generally, method 2, the flow-weighted concentrations method, is the one that is considered to be the best of all of these techniques. The RPLF model or method basically develops regression equations representing the relationship between the pollutant concentration and the flow and magnitude of the flow. In that way, it's somewhat similar to the Flux method, because the Flux method does something very similar to that. Using that relationship, you can predict what the load is going to be on days when the water quality samples are not taken. And that's, again, the basis for the Flux model, to take a relationship between flow and concentration. When the concentration is available, samples are taken, you have flow and concentration taken, and you develop that relationship between flow and concentration. And then you can use that when you have flow to be able to predict as to how much concentration is occurring. The accuracy of that prediction is really the issue associated with how accurate the method really is. And I might mention here there can be some bias in the data because of the large range in values of the water quality variables. And there's an additional technique here for this RPLF method called the minimum variance unbiased estimator approach that can be used to remove some of the bias that's mentioned here. We'll not be using RPLF in the course, but there is a reference it's given here that you can use to find out more information about it. The Flux model is, going back to the Flux model, it's one of the most popular methods that's used for doing load estimation. And currently it's used by the MPCA for doing exactly that. And I believe that they also provide some funding to the person that developed the Flux model to keep it updated. The last of the Category 1 assessment methods is to use literature values to estimate loads. So here you would calculate load coming from a watershed based on land use and some representation of what load rates, load per unit area would be. These involve the use of, basically this method involves the use of export coefficients, and these coefficients are dependent on regional location, soil type, vegetation, precipitation conditions in that particular region, the characteristics of the source of the pollutant. And to be able to apply it, you do need to have these regional export coefficients that are available, and the number of them have been, these tables of these export coefficients have been published. So with this approach, a model called a simple model was developed, or a simple model represents this kind of an approach. Here we're calculating the loads using empirical relationships, and a publication or reference for this is the one by Schuler from 1987 called the simple model. And this model uses tabulated regional load data, loading rates data that are derived from monitoring or experiments, and from that you're able to estimate the load coming from an area that's composed, maybe a watershed that's composed of a number of different land uses. So there's just an example of one of these export coefficient tables. So you can see here, for instance, the line with corn shows nitrogen export coefficient in kilograms per hectare per year was 11.1. The nitrate loading was 2,220. The percent of nitrate load is 11.24. Phosphorus, and they have the same thing for phosphorus here. So these can be used if you had a cornfield area. It may not be 200 hectares in size, basically, as indicated in the table, but the values for the export coefficient could be used to quantify how much is coming from an area. Now, this has nothing to do specifically. This would have to be used with great care, because this would not be associated with as you can see, anything to do with the amount of rainfall that occurred, how much evaporation is occurring, what the water balance of the field is. Doesn't say anything about the soil type. So that's why this might only be applicable to a particular region, where within that region the rainfall is going to be the same. So you could actually apply it to another field that has similar conditions. So the export coefficients can be expressed as load per unit area per year, or load per area per unit of runoff depth. The second of those units, load per area per unit of runoff depth, might be more useful, because there you'd be able to apply that more broadly to areas where you have high runoff depth, areas where you have low runoff depth associated with the amount of precipitation or the type of soils that you have. And some sources for export coefficients. This is not very much information here. There's other publications that have information like this available, and it would be useful if, because of the amount of a massive amount of data that's been collected from areas that have got runoff, pollutant source, pollutant concentration, and so on, somebody could take data from the literature and derive their own export coefficients. Okay, so that's going to end this video where we talked about Category 1 methods. We'll go on, and the next video will cover the topic of